All right, welcome back. Let's continue talking about the properties of definite integrals. Here we have a handful of examples using geometry along with those properties of definite integrals. So I like this example because A, it's a good refresher with geometry, and B, it really stresses how to use those properties that we talked about. The zero width interval, additivity, the constant multiple, the sum difference, all of those. Okay. Limit reversal also. Forgot that one. So let's see. We have basically just a graph, and then there's some points here to give us some reference points as far as to when we're using our geometry to how to find the height of a triangle and the base of a triangle, all that kind of stuff. The height of this semicircle and whatnot. And basically, we just need to go from there, using geometry. And just remember, if you're going to use geometry, the lower limit of integration has to be less than the upper limit of integration. So if that's ever the case, then we'll have to do the limit reversal property. Okay. So let's see. The definite integral from 0 to 2. Okay. And since we have a picture to go off of, geometry is the way to go here. Let's see. So 0 to 2. So 0 to 2 is what? Well, 0 to 2 is a quarter circle. Okay. 0 to 2 is a quarter circle, so I'll just kind of shade it here. All right. So notice that the radius is what? Is 2. So the area of the entire circle is, well, pi r squared would be 2 squared times pi. So pi times 2 squared would be the entire circle. All right, so what, 4 pi would be the entire circle? But we only want a quarter of a circle. So it's 4 pi over 4. Pi r squared is 4 pi. 2 squared times pi over 4, so just pi. Okay, it might help to label these. Here, let's just go ahead and label that pi. Okay. Now what else do we have? 0 to negative 2. 0 to negative 2. So 0 to negative 2. Okay. Notice that 0 is not less than negative 2. Remember, A needs to be the least value. Negative 2 is definitely to the left of 0. So we need to use the limit reversal property and say this is equal to the definite integral from negative 2 to 0 of f of x dx. F of x dx. But we need a negative sign out front. Because why must we do this? Because we're about to use geometry. Okay? So now what's the definite integral from negative 2 to 0? Well, okay, that's the other quarter of our semicircle. Here, let's do this in a different color so we can keep everything kind of color coded. Yeah. So let's see here. That is this region. And again, just by symmetry here, we no reason to reinvent the wheel here. That also has a definite integral pi, an area. Well, area is equal to definite integral because these regions are both non-negative. But remember, as far as our answer is concerned, we have a negative sign out front, and so this is going to be negative pi. Okay. So even though, like, geometrically, those two regions have an area pi, those two definite integrals are different because the second one did not have the situation when a less than b. The lower limit of integration was not less than the upper limit of integration. Therefore, we had to swap them. All right, let's see. Negative 5 to 2 is example C. Negative 5 to 2. So here is negative 5. Okay, so it's this triangle. Okay, now do notice that this triangle is completely below the x-axis. So this we do have the situation where the lower limit of integration is the least number, so that's fine. Nothing to do here. But we do need to note that the entire triangle is below the x-axis. Here, let's get a different color here. Let's do this in blue, I suppose. So since this entire region is below the x-axis, that tells me that my answer is going to be the opposite of area. Now, of course, the area of that rectangle is some non-negative number, but we're not tasked with finding area. Here we're tasked with finding the definite integral. But let's first find the area, because that'll tell us our answer for definite integral with a slight modification. Okay, so let's see. The base of this rectangle, well, I guess you can orient it however you want to. I'll say the base is this distance right here, which is what? It has a distance of 2, because the y value there is -2, which means it has a distance of 2. And then what? We have from -5 to -2, so that's a distance of 3, I suppose. 3, right? From -5 to -2 has a distance of 3. So if we do base times height, however you want to orient it, it's 2 times 3. So 6 divided by 2 is 3. So here, say the area equals 3. And by the way, I should do that for the other two. Let me change those real fast. I'm gonna write these down as areas. So area equals, and then again area. Okay. So the area of that blue triangle is 3. But as I was mentioning before, that entire blue triangle is below the x-axis. So remember, net area, which is what a definite integral does, a net area takes the region above the x-axis and subtracts off the region below the x-axis. You take the difference of those two areas. So there is no region above the x-axis, so we have 0 minus the area of the region below the x-axis, which I think we said was 3. So it's -3. A definite integral that describes a region entirely below the x-axis will always be the opposite of area. Okay? What about 2 to 4? Okay, 2 to 4, we have another shape over here, so let's get a different color. We'll need green this time. So from 2 to 4, we have this region. Now that's a triangle. That's a triangle, so let's see. The base is 2 to 4, so that's 2. And the height is also 2. So the base, if the base is 2 and the height is 2, well, you have 2 times 2 divided by 2. So I guess you have an area of 2. Since 4 minus 2 is the base, 2, height is this y value 2, yeah, so the area is 2. Okay, now the definite integral from 2 to 4, okay, we're using geometry, and the lower limit is lesser than the upper limit, so we can use geometry right away, and that function's completely, that region is completely above the x-axis, so we can say area is equal to definite integral, and yeah, we're just done. 2. So since the region sits entirely at or above the x-axis, area is equal to definite integral. Okay? Now we have 3 to 5. Okay. So we have to split this up a little bit. So 3 is right there, right in between 2 and 4, and 5 is right there. Here, let's find that little triangle first. Need a new color. Do we have another color? Oh, we have yellow, yes. Yellow. Okay, what about this right here? Okay. It's certainly another triangle here. Now the base, I'm thinking about this as like being an upside down triangle. So the base here, this distance is 1, and this distance is what? 2, because the y value there is -2, so that distance is +2. So we have 1 times 2, 1 times 2, divided by 2 to give you the area of the rectangle. That gives us an area of 1. I wonder if that's going to show up nicely. Yeah. Area equals 1. 1 times 2 divided by 2. Now, notice that sits entirely below the x-axis. So if you're talking about a definite integral, well, then it would be a negative one. But the area is always a non-negative measure, so area is positive one. Now let's go back to example E and see what we actually need to figure out. So we need to figure out the definite integral from 3 to 5. Here, so I'll just draw a black line here. 3 to 5. So it's basically this situation. Now remember, what does a definite integral do? It does net area. So net area would be the area of the region at or above the x-axis minus the area of the region below the x-axis. But what do you notice? They're both identical. And we can verify that by noticing we found the area of the green was 2. And we're looking at half from 3 to 4 is half that area. So that'd be 1. And the area of the yellow was 1. So the area above is 1, the area below is 1. 1 minus 1 gives you a 0. Okay? And then what else? Oh, -5 to 5. That's the entire thing. Yeah, -5 to 5. Okay, so -5 to 5, let's think about this. The net area, which is what a definite integral does, is the sum of all of the regions above the x-axis. So let's do that first. Let's go in order, actually. Let's go in order. So you add positive the areas of the region above the x-axis, and you subtract the area of the region below the x-axis. So this first one, blue, the blue triangle, is entirely below the x-axis. So we need to subtract it, -3. Okay, then the red, it's above the x-axis, so we're going to add it. The black area, it's above the x-axis, so add it. Green, it's above the x-axis, so add it, +2. And the yellow, below the x-axis, so subtract it, so -1. And then what do we get if we do a little simplifying here? We have what? Pi plus pi is 2 pi. Then we have -3 plus 2. That's -1. And then we have, okay, -1 minus 1. That's -2. We get -2 plus 2 pi. Cool. -2 plus 2 pi. All right. Ooh, I like this example. The definite integral from -5 to 5 of f of x plus 2. All right. Now here's the thing. Geometrically, what does this do? Geometrically, this takes the graph and raises everything by 2 units, translates everything up 2 units. Now, I suppose we could try to redraw that graph with everything shifted up 2 units, and then we would have a bunch of different shapes. Like we would have not at all the shapes we have now. Like we would in the middle, we would have like a rectangle with a semicircle on top of it, like we saw in a prior example. And we would have different shapes, maybe some rectangles and triangles we'd have to work with. But I think we can avoid redoing all that geometry because we can use properties of definite integrals, which says if you have the definite integral of 2 or more functions added together, you can take the definite integrals individually. By the way, I've given this exact question on a test before, like with a similar picture, but like basically the exact same question, and like nearly the entire class misses it. And I'll show you what almost the entire class will do. And in fact, I'll probably give it a question like this on your test, on the upcoming test you're going to take. And here's what probably 95% of the class will do. This is equal to the definite integral from -5 to 5 of f of x dx plus 2. And I know that, okay, there's my previous answer. Okay, so it's -2 plus 2 pi plus 2. So I get, what? -2 and +2, so I get 2 pi. Okay? And that's what a large percentage of a class will tell me on any given semester. Where did I go wrong? Why is that not right? Well, it turns out the first step is what's wrong. That is what's wrong. Why? Because it's not the definite integral from negative 5. Oh, well, first of all, that's obviously wrong. There's not supposed to be a negative sign there. Negative 5 to 5. Okay. It's not the definite integral from negative 5 to 5 f of x dx plus 2. It's the definite integral from negative 5 to 5 f of x dx plus the definite integral from negative 5 to 5 of 2 dx. The sum difference rule says you can break apart into two separate definite integrals. We can't just add 2. It's the definite integral of 2. Okay, so now I can say, all right, I know that this was the answer to part F. So negative 2, assuming I did it correctly, negative 2 plus 2 pi. So I'll put that in parentheses. But then I have to do this second definite integral, but it's a constant. So I can use a separate picture, separate geometry to figure it out because it's plus 2. It's a constant function 2. Let's put 2 right there. It looks like so. If I want the definite integral from negative 5 to 5, guess what I have? I've seen this picture now several times, or a similar picture. I have a rectangle. And a rectangle is super easy just to do by geometry. What's the base? So plus the base is 10 times the height is what? 2. That's base times height, and it's positive because that region is at or above the x-axis. If it was like a negative 2, then the answer would be negative 20. Okay, so equals, well, I have negative 2 pi, and then I have, oh, what did I do that for? I make so many copy errors here. You're probably asking me, like, what the heck is going on here? Why do you write 2 pi and 2 pi? It's negative 2 plus 2 pi. Okay, so I have negative 2 plus 20, that's 18, and then plus 2 pi. Again, because I had to find the definite integral of a constant function, which, again, always is going to be a rectangular shape. Okay? The last one here, and we've talked about absolute value before, but it's important to keep coming back to this topic because you have to have a geometric intuition when you're doing this to remember what absolute value does to a function. So let me pick a. Do I have a new color? Do I have a new color I can use? Oh, I can choose a new color, I believe. Yeah, here's pink. Here's a pink that will be hopefully different enough for us. What does absolute value do to a function? Absolute value, or to a graph, is absolute value takes anything that was below the x-axis and reflects it across the x-axis. So, for instance, this point over here, negative 5, negative 2, it was originally below the x-axis. Absolute value flips it up over here, and now we have the point negative 5, positive 2. And so instead of having this blue triangle down there, well, now we have a exact same triangle, except it is above the x-axis. That's what absolute value does. And then notice, okay, the red region was already at or above the x-axis. Black region was already at or above the x-axis. Green triangle was already at or above the x-axis. But then you go over here to this yellow triangle, it was below the x-axis. So absolute value takes that 0.5, negative 2 and flips it up here to 5, positive 2. And so we have instead this triangle. Okay, so absolute value is now everything that's above the x-axis. So as far as absolute value is concerned, we forget about. Here, let's see. Yeah, forget about this, and forget about that. We're only concerned with what's happening above the x-axis. So everything now is non-negative. So all the areas can be counted in a positive fashion because everything is now above the x-axis. Now I should now go back and add what is the area. Well, the area of the left-hand pink triangle is still 3. The area is still 3, just like the area of the blue is 3. But their definite integrals are different. Again, area here is still 1, just like the area of the yellow triangle. The difference is being the definite integral of the pink triangle on the right is different than the yellow triangle because the yellow triangle was below the x-axis, so it had a -1 definite integral. Pink is above the x-axis, so it has a +1 definite. And this question really stresses the difference between area and definite integral. Because absolute value makes everything positive, and so you have a bunch of positive regions to work with. So now we can simply go and write the sum of those regions. And so we have what? The first one is 3. The red region was pi. The black region was pi. The green triangle was 2. And the pink smaller triangle was 1. So notice it almost looks exactly like this, except we're not subtracting anything because we have reflected those regions that were negative, the blue triangle and the yellow triangle, we've reflected them above the x-axis and now made them positive. So we're still going to have that 2 pi since there's 2 positive pi's, but now we have 3 plus 2 plus 1, so 3 plus 3, so we have 6 plus 2 pi. And there we are. Okay, so absolute value, just remember, it reflects things that were below the x-axis, reflects them above the x-axis with some nice symmetry. And so we can still use geometry, but we have to be careful when we have absolute value involved. Okay? All right, you will definitely have homework questions like this. Perhaps a quiz question, perhaps a test question. I'd say probably for sure a test question because I always ask some sort of geometry, definite integral via geometry type question. And I like to ask questions on a test or exam that really test to make sure that you have straight in your head what's the difference between area and a definite integral. And the key being is area equals definite integral if the region's at or above the x-axis, like the red region or the black region or the green region. But if the region is not at or above the x-axis, then the definite integral equals the opposite of area. For instance, the definite integral of -5 to 2 is -3, the opposite of area. The area was 3. Likewise, the definite integral from 4 to 5, that is the yellow rectangle, sorry, the yellow triangle, the definite integral is -1. But the area, of course, has to be a non-negative measure, which is +1. In other words, area is almost always positive, sometimes it's 0. Definite integrals can be negative, positive, or 0. And I hope that you really let it sink in and of course do all the homework that gets to that fact and such. Okay? Always feel free to reach out. We'll catch you in the next video.